Hello, my name is Steve Miller and I'm the product manager for the Simscape product family at MathWorks. In this presentation, we're going to see how you can model and simulate mechatronic systems with Simscape Electrical. Here are the key points about Simscape Electrical that I would like you to remember. First, we'll see that Simscape Electrical provides mechatronic and electronic component models for system-level simulation. You can model electromechanical actuation systems, including the motor and the drive circuitry, and you can model analog circuits. You can model many other types of electrical systems with Simscape Electrical. The models you use can be customized to meet your needs. You can adjust the parameterization options via drop-down menus so that you can specify the behavior in a way that's convenient for you. You can also add or neglect physical effects. You can connect your electrical networks to thermal networks to see the effect of heat transfer on your system. You can also modify the equations directly using extensions of the MATLAB language. And you can leverage MATLAB and Simulink. You can use these models to perform system-level analysis, where you optimize your integrated electrical, mechanical, and control systems. And you can use them to perform control design and hardware-in-the-loop testing, where you test embedded hardware and software without relying on hardware prototypes. Here is the agenda for our presentation. We'll first take a look at a couple of example applications and tasks where Simscape Electrical is used. We will then build up the model of an Aileron actuator. We will assemble some components to put the system together and estimate parameters in the system based on measured data. We will then refine the model. We will adjust model fidelity based on the task we need to perform and define a custom component using extensions of the MATLAB language. We will then optimize the system-level design and then perform hardware-in-the-loop testing on a real-time system. Simscape Electrical is used in a wide range of industries and applications. We will take a look at an actuation system. An actuation system attempts to track a speed profile. A DC motor drives a worm gear via a lead screw. The speed controller is implemented as an analog circuit, and it is connected to a motor servo amplifier that controls the voltage applied to a DC motor. Here you can see a portion of the Simscape Electrical model, including the motor, the drive circuitry, and a portion of the analog circuit that implements the speed controller. To ensure that this model yields realistic behavior, you can enter parameter values directly from datasheets. You can also use this model to evaluate thermal effects. How does the change in the behavior of the components as they heat up affect overall performance? And we can assess the effects of hardware implementation. How do nonlinearities in the sensor affect overall system behavior? Simscape Electrical is used to select motors and drives, evaluate circuit architectures, and design control systems, including hardware-in-the-loop testing. I'll now switch over to the model so you can see what this looks like. Here's the model of our linear electric actuation system. A DC motor drives a lead screw through a worm gear. At 3 seconds, a load is applied to the lead screw, and the control system attempts to accommodate for that. On the scope, we can see the speed of the system, including the effect of the disturbance. The pink line is the exact speed of the motor, and the yellow line is the speed as reported by the sensor. If we look at our model, we can see how the DC motor was parameterized. Here you can see we have chosen to parameterize it using equivalent circuit parameters. We could have specified stall torque and no-load speed, or rated power, rated speed, and no-load speed. These are all values commonly found on datasheets, and having options allows us to pick the one for which we have the best information. If we look at the control circuit, we can see that the speed controller was implemented as an analog circuit, using band-limited op-amps, resistors, capacitors, and other components. The current controller was also implemented as an analog circuit. You can see the same components here. The effect of hardware implementation is also captured. Here we have an incremental shaft encoder, which is what is used to sense the speed of the motor and provides the signal that is given to the speed controller. We saw on the scope that there are delays and quantization effects from this sensor, so we can use Simscape Electrical to determine the impact of those effects on overall system behavior. Our motor driver has been implemented in 2 ways. We have an abstract model of our driver circuit. We have a controlled PWM voltage and an H-bridge. The H-bridge applies the voltage to the DC motor. Both of these blocks have been configured to run in averaged mode. In averaged mode, the voltage applied to the DC motor varies smoothly from 0 to the supply voltage. We can configure these components to run in pulse-width modulated mode. When it runs in pulse-width modulated mode, The voltage that is applied to the DC motor is a pulse width modulated signal. The width of the pulse varies with the magnitude of the duty cycle. Using this, we can see the effects of pulse width modulation on system performance. The other variant of our drive circuit has much more detail. If we click on this, we will configure the motor driver circuit to use a full circuit implementation. We have used opto-isolators and MOSFETs to model the entire H-bridge. This is a much more detailed model and would allow us to explore even further detailed effects of the drive circuitry. We are now using a MATLAB script to rerun the simulation with this more detailed variant and produce a plot that will show us a little bit more about the behavior in the system. Here we can see the plot of the voltage applied to MOSFETs on one side of the H-bridge. We can see that both are conducting at the same time, which results in a power spike. This is information that the circuit designer and the algorithm designer would like to know so that they can try and avoid this power spike or determine its impact on the system. We can also include thermal effects. If I right-click on this block and go to the Block Choices option, I can enable a thermal port. Here you can see an orange port, which allows us to represent a thermal network. By typing in heat transfer, Quick Insert allows me to insert a convective heat transfer element, so I could include the effects of heat transfer to the environment in my system model. Enabling this effect also includes an additional tab for temperature dependence. This allows me to modify the behavior of the motor based on the temperature of the motor itself. In this example, we have seen the many different aspects of how we can use Simscape Electrical to model a mechatronic system. Simscape Electrical can also be used in automotive applications, such as hybrid electric vehicles. In hybrid electric vehicles, a number of different kinds of systems come together, including electrical motors, generators, batteries, and combustion engines. Simscape Electrical can help you model this system. You can use it to test for integration issues between these different subsystems, design the control logic, and to optimize system-level performance, such as maximizing fuel economy. I'll now switch over to the model so you can see what this looks like. Here is our model of a hybrid electric vehicle. The electrical system has been modeled using Simscape Electrical, including the motor, generator, DC-DC converter, and the battery. The model of the motor and the generator abstracts the torque speed behavior of the motor and the motor driver. This enables a very rapid simulation, ideal for system-level testing. The battery model has been modeled as a generic model, which can be parameterized to match many different chemistries. If you would prefer to create your own model of a battery, you can use Simscape components to create an equivalent circuit model, or you can use Simscape language. With Simscape language, you can implement your own equations directly and specify the exact behavior you would like to have. The model of the electrical system has been connected to a mechanical model of the vehicle dynamics, modeled in Simscape Driveline. Here you can see the vehicle dynamics, the tires, differential, and other components. This is connected to the control system. The control system includes a model in Stateflow that models the logic that controls which mode the hybrid electric vehicle is in. Simulink has been used to model the controller for the engine speed, generator, motor, and battery charge controller. When we run the simulation, as a system-level model, it runs very quickly. This is a plot of the vehicle speed as it runs through a standard drive cycle. This is about 3 minutes worth of simulation, which runs through very fast. We can look at the scopes to analyze some of the other behavior in the system. We can see the temperature of the DC-DC converter as it climbs during the simulation, and we can see the voltages on the DC bus and on the battery. If we would like to look at more simulation results, we can use the Simscape Results Explorer. The Simscape Results Explorer stores all of the simulation results from the Simscape network, and you can explore it in a tree browser. If we go back to the model of the motor and look at the results, we can see the speed it was running at, the current, the power dissipated voltage, and other aspects of the simulation results. This model of the hybrid electric vehicle incorporates many different subsystems and can be used to detect integration issues and design the control system. Now we will build up a model of our Aileron actuation system. Our Aileron actuation system consists of a three-dimensional mechanical model of an aileron with an actuator that extends and contracts. A control system is attempting to match a desired angle. It does that by extending and contracting the actuator, so it needs to determine the amount of force that needs to be applied. We would like to use this model to achieve a number of goals using simulation. We would like to use it to determine the requirements for the actuation system. How much force must it apply, and how quickly must it react? We would like to test different actuator designs. We would like to optimize system-level performance while ensuring that we meet system-level requirements, and we would like to run the simulation on real-time hardware for hardware-in-the-loop tests so that we can test the embedded hardware and software without using hardware prototypes. I'll now switch over to the model so you can see the starting point for our design. Here is our model of the Aileron actuation system. Here we have the mechanical model of the Aileron, which has been imported from a CAD system. You can see the joints and the parts modeled in Simscape Multibody. This is connected to our model of the actuator. At this stage, we have an ideal actuator. We don't really know exactly what the design will be like. We're assuming that our actuator can provide as much force as we need as soon as we want it. When we run the simulation, we can see how well the system tracks a reference angle. A 3D animation of the simulation results is shown here, and here on the plot we can see how well the aileron is tracking the reference angle. The reference angle is shown here in blue. This ideal actuation system allows us to determine some of the requirements for our actuator, such as how much force we need to provide. This is useful information as we begin to design our electromechanical actuation system. In this demonstration, we will see how to use Simscape to model an electromechanical actuator. The model we wish to build consists of a DC motor that drives a lead screw via a worm gear. The lead screw extends and contracts. The DC motor is controlled by a motor servo amplifier. We need to determine the required size of the actuators in our system. We will use Simscape to do it. This is a portion of the model that we will build, where you can see an abstract model of the drive circuit, the motor, and a portion of the mechanical system. We will connect this to a three-dimensional mechanical model in Simscape Multibody to see if our actuator design is strong enough to raise and lower the aileron. I'll now switch over to the model so you can see how this is done. To start, we'll use the command sscnew to open up a new Simulink model with the settings recommended for Simscape models. To begin, we'll need a DC voltage source. So we'll type in DC voltage source and pick a source from the list that is offered by Quick Insert. We'll set the supply voltage to 24 volts. We're going to drive our DC motor with a PWM voltage. So we'll click and drag a line and type PWM and select a PWM voltage source. We'll need a ground block, so we'll click and drag to create a line, type in ref, and get an electrical reference. Simscape uses solver technology above and beyond what's available in normal Simulink. So to have access to those settings, we'll connect the solver configuration block. The next thing that we'll need is an H-bridge. This will be the driver circuit for our DC motor. So I'll click and drag a line and type H-bridge and select that component. These two blocks can be configured to run in averaged mode or PWM mode. In averaged mode, the driver voltage varies continuously from ground to the supply voltage. We're going to select averaged because that will result in a faster simulation. For our early system level testing, this is appropriate. We could use PWM mode in a later stage when our design is more complete. We'll connect the rest of these pins to ground for now. We're not going to run the motor in two directions at this stage. The next thing that we need is the DC motor itself. I'll click and drag and type motor. We can see there are quite a few motors to choose from. We'll select a DC motor. We'll connect the ground, the minus pin to the ground, and we'll connect the minus side of our H-bridge driver to ground as well. This completes the electrical portion of our model. Now we need to create the mechanical portion. These ports represent the mechanical connections on the motor. I'm going to connect the housing to a point fixed in space, so I'll click and drag, type in ref, and get a mechanical rotational reference. We're going to need to use a gearbox to give our DC motor a bit more torque. So we will type in gearbox, and we'll set the gear ratio to 1/5. Then we'll connect it to a lead screw in order to translate the rotational motion into a translational motion. We'll use a wheel and axle block to make that conversion. Then we will use this to drive a mass. So I'll click and add a line, type mass, and select the mass block. So at this point we have our electromechanical system. I will run the simulation, and we can right-click on the mass block to see what the simulation results are. We'll select Simlog. The Simscape Results Explorer will open, and we can see that this actuator is able to move our mass. Now we're going to bring in the model of the aileron. In our library of components, we have a pre-assembled subsystem that has the mechanical model of the aileron. So I will attach this here and remove the mass block. When I update the diagram now, we'll be able to see the three-dimensional mechanical model of the aileron. We'll view it from the side, and we'll set the background to be white to make it a little bit easier to see. Now we're only using default values, so when I run the simulation, I don't expect the aileron to move, because I don't expect it strong enough. And we can see that the aileron is simply swinging under gravity. Our motor is not remotely strong enough to move it. So we'll make a quick adjustment to one of the parameters just to get it to move. We'll go in and set the back EMF constant to 40. It's a very large adjustment, but this should be strong enough to get it to move. Here we can see that the actuator is driving the aileron downwards. And if we switch the direction of the wheel and axle from drives in positive to drives in negative direction and rerun the simulation, we can see that the actuator is contracting and raising the aileron. So we have our initial design for the electrical actuator. We haven't set any parameters yet, but we can use measured data to do that and improve the design. In this demonstration, we have seen how to model an electromechanical actuator using Simscape. In this demonstration, we're going to see how to estimate parameters in our model using measured data. We have a model of a DC motor driven by a motor servo amplifier. These are the results of our simulation. When we compare it to measured data, we see that they don't match. And this is our challenge. Our simulation results do not match measured data. We're going to use Simulink design optimization to automatically tune these parameters until the results of simulation match the measured data. These are the parameters we need to tune. We will use optimization algorithms to automatically adjust these parameters until the results of simulation match the measured data. Here are the steps we'll go through. First, we'll import measured data and select the data we will use to perform the estimation. Then we will identify the parameters and their ranges, and then we will perform the parameter estimation. I'll now switch over to the model so you can see how this is done. Here is our model of our electromechanical actuation system in a simplified form so we can verify its behavior. When we run the simulation, we can see that the results of the simulation in yellow don't match the measurement results in pink. The reason that doesn't match is because the parameters haven't been set properly. When we look at the blocks themselves, we see that we have used MATLAB variables to set these values. We're going to tune these MATLAB variables until the results of the simulation match the measured data. We're going to use the parameter estimation UI in order to do this. Here you can see the measured data that our simulation results need to match, and this is the signal we're using to excite the motor. Here's where we'll see the evolution of the parameter values. These are the MATLAB variables we need to tune. Here we've selected the ones we wish to tune and define their ranges. Now that we have the measured data, have selected the variables, and defined the ranges, we'll perform the estimation. During the estimation, Simulink response optimization is running the simulation, varying the parameter values, looking at the results of the simulation, and determining whether the changes it made improved the results or made it worse. Using optimization algorithms, it can decide which direction to change the parameter values in. You can see that the simulations are running extremely quickly. We are using fast restart in order to accelerate this process. This allows it to skip over the initialization phase and jump right into simulation. You can see that after this short period of time, the simulation results are much closer to the measured data. Our estimation is complete. We can rerun the simulation and see what the final result looks like, and we can see that the simulation results match the measured data very closely. In this demonstration, we have seen how we can use measured data to improve the accuracy of our physical model. Now that we've seen how to build our model and adjust the parameters to make it match reality, we will look at some of the other options we have to to adjust the fidelity of our model. There are a wide range of components provided with Simscape Electrical for mechatronic applications. The semiconductor models are appropriate for applications involving switching and signal amplification. You can parameterize them based on datasheets. They also include simple and detailed variants, so you can include just the amount of effects that you need. You can adjust the models to include thermal effects. You can model the effective temperature on the behavior of the individual devices. You can also model heat transfer to the environment, so you can model the evolution of temperature for the components in your system. You can also measure power losses at any level of your circuit architecture using MATLAB commands. In addition to the individual devices, there are power converter components that combine many of these devices together for common power conversion applications. The motors library includes a wide range of translational and rotational actuators. You can parameterize these models using datasheets or with data from finite element software. You can also specify electrical losses. You can include thermal effects on your systems with motors. You can model temperature-dependent behavior of your motors and model heat transfer to the environment. You can also include or neglect switching effects. You can run an averaged mode to neglect the effects, or switch to pulse width modulation mode to see how switching will affect the overall behavior of your system. The libraries include single-phase, three-phase, and other types of machines. The components in the sensor library cover a wide range of applications. This includes electronic, thermal, and mechanical sensors. Analog and digital sensors are provided with a number of parameterization options. You can include or neglect a number of effects, including sensor bandwidth. You can also test the effects of sensor damage or failure on system performance. You can include effects such as backlash in your system, and you can make basically any component fault or fail using the generic fault block. This enables you to test whether your algorithms are going to be robust to failures in your system. The op-amps and logic libraries include behavioral models for fast simulation. These provide similar behavior to models that have a transistor implementation. Because these models are abstract, they simulate extremely quickly. This enables you to test larger circuits in a shorter period of time. You can use these models to perform high-level design, such as how to avoid nonlinear effects during normal circuit operation. The passive devices library includes a range of linear and nonlinear devices. In these devices, you can enable physical effects, such as noise and saturation. You can specify operating limits on a number of the passive devices. This allows you to model realistic behavior. You can trigger any component in your circuit to fail based on conditions in the circuit or simply based on time. We have seen a number of options for adjusting the level of fidelity in the components in your model. Now we'll look at an example where we adjust the level of fidelity and see its effect on the behavior of the system. In this demonstration, we'll see how to balance the trade-off of model fidelity and simulation speed. We have created a model of an actuation system. We made a number of assumptions during the design process, and we need to determine the impact of those assumptions. We designed the control system using pure Simulink. This abstract model runs very quickly and allows us to use linear control theory to design the control system. However, in the final implementation, it will be an analog circuit. We need to determine the impact of the changes due to the hardware implementation on the performance of the system. In development, we drove the motor with an average signal. However, in the final design, the motor will be driven by a pulse width modulated signal. Our challenge is to assess the effect of design implementation on system performance. We will use Simscape Electrical to do it. We will switch from a Simulink implementation of the controller to an analog circuit and verify its effect on system-level performance. We will also switch from averaged mode to pulse width modulated mode to drive the motor with a pulse width modulated signal and see the impact that it has on the current, the torque levels, and the losses in the system. I'll now switch over to the model so you can see how this is done. Here is our model of the Aileron actuation system. The mechanical model of the Aileron was imported from a CAD system and is modeled in Simscape Multibody. The electrical actuation system was modeled in Simscape Electrical. Here you can see we have 3 electrical lead screws on the same electrical circuit. These lead screws extend and contract in order to raise and lower the aileron. These lead screws can be configured to have more detail or less detail depending on the task that we are performing. Inside each lead screw subsystem, we find the motor driver circuit, and the control system. Currently, the control system is configured to use a Simulink implementation of the control algorithm, a very simple algorithm that we can use with linear control theory. We can configure this model to use a circuit implementation. When we enable this variant and we go in, we can see that the control system has been implemented with an electrical circuit, with frequency-limited op-amps, resistors, capacitors, and other components. The current controller is also implemented using an analog circuit. We can also adjust the fidelity of the motor driver circuit. Currently, the motor driver circuit is configured to run in averaged mode. In averaged mode, the voltage applied to the motor varies continuously from 0 to the supply voltage. We can configure this to run in pulse-width modulated mode. When configured to run in pulse-width modulated mode, the motor will be driven with a pulse-width modulated signal. We can also configure the driver circuit to be an analog circuit with power electronic components. In this version, we have an H-bridge modeled using MOSFETs. This is a much more detailed variant of the driver circuit. We'll reset these to the most abstract level of fidelity. We'll run a MATLAB script to compare the abstract and more detailed variants. We'll see the results on a scope and on a figure window. Here you can see the 3D animation of the results. We have now tested this with the abstract Simulink implementation of the controller. Next, the MATLAB script will configure this to run with the circuit implementation. And we'll see those results plotted on the scope, and we will overlay them on the MATLAB figure window. We can see that both track the reference signal fairly well, but there is an impact from the hardware implementation on both the angle and the force applied. Now we'll do a comparison between averaged mode and pulse-width modulated mode. We've run this for a much shorter period of time so that we can see the results quickly. When we overlay the simulation results, we can see that the angle is the same. However, the motor current is much different. The higher levels of current running through the motor and the rest of the system have an impact on the losses of the system. If I right-click on the block, select View Simulation Data, and select the SimLog variable, we can see the simulation results in the Simulation Results Explorer, and we can see the power dissipated over time. We can use a MATLAB command to get a full summary of the power dissipated at this level of the circuit. Using the command electGetPowerLossSummary and citing the appropriate level of the electrical circuit in the SimLog variable, we get a table summarizing all the components that have dissipated power and the amount of power dissipated over the period of the simulation. In this demonstration, we have seen how we can balance the trade-off of model fidelity and simulation speed. We have seen many ways to adjust the level of fidelity of our Simscape Electrical model. Now we will see how we can adjust the level of fidelity at the equation level. In this demonstration, we'll see how to model custom physical components in Simscape. We have a model of an analog circuit. The behavior of some of the components in our circuit is dependent upon temperature. We wish to include these effects in our model. We will use Simscape and MATLAB to do this. This is the equation that models the behavior of our component. With these parameters and this equation, we can create this new component. The code we use to create this component is based on MATLAB, it's object-oriented, and it allows us to define implicit equations, DAEs and ODEs. I'll now switch over to the model so you can see what this looks like. Here is our model of an analog circuit that represents a filter. When I run the simulation, we can see what the gain of the filter is. This block is where we specify the temperature. If I change the temperature to something different and rerun the simulation, we will see that it has no effect. We can see that the gain has not changed. I have a custom component that takes into account the effect of temperature. With this hyperlink, I've replaced the two resistors with this custom component. When I rerun the simulation, we see that the gain has changed. If I increase the temperature and rerun the simulation, we see that the gain changes again. Taking a closer look at this component, we can see the parameters that I have used to specify it, and here is the Simscape language code with the equations that take into account the effect of temperature. Let's take a closer look at this code. Here is our custom component. This resistor needs two electrical ports, the plus and minus side of the resistor. Here's the portion of the code that defines them. We reuse the domain definition from Simscape so that we can connect this custom component to the rest of the electrical libraries in Simscape. It would also have been possible to define a new domain. In the next step, we define the user interface. Here are the parameters that we wish for users to be able to change, and here is where they're defined. The parameters, the units, and the dialog box text are all defined within the Simscape language file. Next is where we leverage MATLAB. This portion of the code checks to see if a parameter value is below a lower limit, it issues a warning, and then resets the value to something that is permitted. In this section, you use functions and expressions that follow MATLAB syntax for typical tasks such as analyzing parameters and performing preliminary computations. This section is where we define how the component behaves, and is what enables us to reuse this component so easily. This equation defines how our resistor should behave with respect to temperature, and here is where we implemented it. The equations here are defined in a text-based language. You can define equations that depend on variables, their time derivatives, parameters, and other quantities. The most important thing to note is that these equations are all solved simultaneously. This is different than equations defined in MATLAB or C, where the commands are evaluated one after the other. Here you define a set of equations, and during simulation all of the equations in the entire network are solved at the same time. The equations you define can be DAEs and ODEs, and assignment is not required. Again, Simscape will ensure that all equations are evaluated to be true at every time step. In this demonstration, we have seen how to define a custom component using Simscape language. Now that we have included all relevant physical effects into our system, we will use optimization algorithms to optimize the performance of our system-level design. In this demonstration, we'll see how to optimize the performance of an electromechanical actuation system. We have an electromechanical actuation system that extends and contracts to position an aileron. It has an inner control loop for current and an outer control loop for speed. When we simulate the system, we can see that it is well within the requirements for the force, but could track the reference angle a little bit better. Our challenge is to improve the performance of this actuation system while meeting the force requirements for the actuator. We will use optimization algorithms to do this. We will use optimization algorithms to tune parameters within the speed controller to have it track the reference angle better while meeting the specified requirements for actuator force. I'll now switch over to the model so you can see how this is done. Here is the model that we're working with. The mechanical model of the aileron was imported from a CAD system, and it is modeled in Simscape Multibody. The electrical system was modeled in Simscape Electrical. Here you can see 3 electrical lead screws on the same electrical network. The control system for the actuators was modeled in Simulink. This enables us to use linear control theory to tune the controller. There are 2 parameters, the proportional and integral control gains. These are the gains that we wish to tune in order to improve the performance of the system and to make sure that we are staying within the requirements for the force the actuator can provide. We'll run the simulation to see how it performs. Here you can see the 3-dimensional animation of the mechanical system, and here you can see that the yellow line, the actual angle of the aileron, is not tracking the reference angle so well. We are within the force requirements for the system, and we have a bit more space so that the system could apply more force to track the reference angle well. To tune those parameters, we're going to use Simulink design optimization. I'm going to open up that user interface now. Here in this layout, you can see the signal that we need to track, the force that the actuator is applying, and you can see the upper and lower limits, and here you can see the trajectory of the parameters we wish to tune. Here are the parameters that we wish to tune. To optimize this, we would simply click on the Optimize button. I'm going to show you a video of the optimization process so we can see it in a shorter period of time. Here in this slide, we see a video of optimizing the performance for this actuation system. You click on the Optimize button, and the optimization begins. Simulink Design Optimization runs the simulation, compares the simulation results to the requirements we have set out, tracking the reference signal and the limits on the force, evaluates the behavior, and then adjusts the parameters accordingly. Using optimization algorithms, it will adjust the parameters in the correct direction in order to improve the response of the system. I'm replaying this at six times actual speed. You can see that the results are rapidly converging towards a point where we are tracking the reference angle of the aileron quite well, and it is staying within the limits we have specified for the force the actuator can apply. In this demonstration, we have seen how we can optimize system-level performance. Now that we have optimized our system-level design, we are ready to test our embedded software using hardware-in-the-loop testing. In this demonstration, we'll see how to configure an electromechanical actuator for hardware-in-the-loop testing. We have a model of an electromechanical actuation system. We are satisfied with the performance in simulation on our desktop computer. We now wish to configure this model for hardware-in-the-loop testing. However, portions of our model are numerically stiff. We will need to configure the solvers to make the model real-time capable and convert it to C code so we can download it onto the hardware-in-the-loop testing system. We will use Simscape local solvers and Simulink coder to do this. Here are the steps we'll go through. First, we'll configure the model to use a fixed-step, fixed-cost solver appropriate for real-time simulation. We will rerun the simulation on our desktop computer and verify we get the same results. We'll then convert the model to C code and download it to the real-time system. We will rerun the model on the real-time system, upload the results, and verify that they are the same. Then we'll perform our test. We will vary a parameter in the system, rerun the simulation, upload the results, and see that it had an effect. I'll now switch over to the model so you can see how this is done. Here is the model that we're working with. 3 electromechanical actuators extend and contract to move an aileron. The aileron is modeled using Simscape Multibody, where we have mechanical parts and joints imported from a CAD system. The electrical portion is modeled in Simscape Electrical. Here you can see the electrical network with the 3 lead screws, and if we go into one of these subsystems, you can see the motor, the gear, the lead screw, and the abstract model of the driver circuitry. We will use a MATLAB script to walk us through the process of configuring this model for real-time simulation. Here you can see a 3D animation of the system. First, we will run the simulation to get a set of reference results using the variable step solver. The results are plotted on this Simulink scope, so you can see that the signal in yellow, the actual angle of the aileron, is tracking the reference signal quite well. And here you can see the animation as the aileron actuator extends and contracts. We'll add the reference results to a figure window. We'll use this to compare with the results with the fixed step solver. We'll now configure the model for fixed step simulation. We have enabled the local solver in the solver configuration block, and here we can see the results on the scope. The simulation is complete. We'll add these results to our plot, and we can see that the results compare very well. If we zoom in closely, we can see that the results from the fixed step, fixed cost simulation are nearly identical to our reference results. At this point, we are happy with the simulation. We believe it is real-time capable. We will set up the runtime parameter. The runtime parameter is going to be friction in the motor. If we open up this block, we can see that this parameter is configured to be a runtime parameter. That means we can change its value without regenerating the code. Now we will build and download the code to the target. Here you can see messages from the code generation process, and here you can see the real-time target where we will be downloading the code. The results from the simulation will be shown on this monitor, which is connected to our real-time target. The model has now been downloaded onto the real-time machine. We will set this up to run in external mode, connect to the target, and run. The simulation is now running. We can see the results on the monitor. We can also see them updating on the scope as we're running in external mode. The simulation is now complete on the real-time target. We will upload the results and add them to our plot, and we can see that we got the exact same results on the real-time target. We also had no overruns, so the model with the mechanical, electrical, and other components is real-time capable. Now we'll run our hardware-in-the-loop test. we're going to modify a parameter in our system. We're going to increase the friction in the bearing as if the bearing is starting to fail. We will now rerun the simulation using the start command. You can see on the monitor that we are rerunning the simulation, and again, we didn't need to re-download the code. We just adjusted the parameter in the physical system right on the hardware. This simulation is now finished. We will upload the results, and we can see that the results from the second test, where we increased the friction in the bearing, are a little bit different. So we see that we are able to run tests in hardware in the loop configuration. In this demonstration, we have seen how to configure a model of an electrical actuator for hardware in the loop testing. In this presentation, we have seen that Simscape Electrical provides mechatronic and electronic component models for system-level simulation. You can adjust the models to meet your needs, and you can leverage MATLAB and Simulink to perform system-level analysis, control design, and hardware in the loop testing.